Yeah, Welcome back to the series of lectures on digital system design. Myself, Rajakishore, Assistant Professor, Department of ECE, Murray Lakshman Reddy Institute of Technology and Management. In the last videos, we were discussed about combinational circuits, basic adder circuits. So in this video, we're going to be discuss about the code converters, and let us recall once again of a binary subtractor circuit also. Yeah. So binary subtractor of a 2-bit subtractor or binary subtractor can also called as an half subtractor, because this particular combinational circuit which can able to subtract two numbers. So as we know the procedure of a combinational circuit, the first one is a problem statement. Here what is our problem statement? I need to design a circuit of subtracting two binary numbers. So that is my problem statement. So that I need to find what is the input and what is an output variables. So any subtractor, I am saying a 2-bit binary subtractor, it is having two variables. I am considering my input variables are like A and B. Okay, my input variables A and B, and I'm taking my output variables like a difference and borrow. And now I want to be design an half subtractor here. So this is the step one. Then once if you find out the number of inputs and outputs, then I need to form a truth table which gives the relation between input and output. So because here I am having a 2 inputs, the maximum possible condition 2 power 2 is nothing but 4 possible conditions are there. So I have written inputs A and B, and the possible conditions like 0 0, 0 1, 1 0 and 1 1 has taken. And already we discussed the any subtractor 0 minus 0 is a difference will get 0 and borrow is 0. 1 minus 0, difference is 1, borrow is 0. Similarly 1 minus 1 is difference 0 and borrow 0. So when we got a borrow, if I'm subtracting smaller number minus larger number, so if I do 0 minus 1, I can get 1 as a difference and 1 as a borrow. So I have found step 2, I found the relation between input and outputs of given problem statement. Once the given find out the truth table, then I need to realize or a simplified expression for the corresponding outputs, individual outputs. So let's take this is an individual outputs, because it is a 2 variable. I have taken K map, so I am getting difference output is A bar B bar plus A bar B. So simply A XOR B, and B naught is nothing but A dash B. So after finding this, I need to be draw. So without simplifying, this is a circuit I have drawn. A bar B bar plus AB, this is your difference. Now I need a combined circuit. I have to be combined. Individually, this is the output I have drawn. So combinedly, I have a half adder circuit is like this. So if I kept inside a square, so that this is an half subtractor. Okay, this is a square box here, half subtractor, where 2 inputs and 2 outputs, it is going to be subtract. Okay, so this is your half subtractor. Then similar manner as we need to go for a full subtractor also. Okay, this is your half subtractor. Then we'll go for a full subtractor. As we said that a full subtractor, because full subtractor is nothing but a 3-bit subtractor. Simply I can say that 3-bit subtractor. So my circuit is like this: A, B, C. Full subtractor, again it is having a sum and borrow, or it is can say that a difference and borrow. Okay, it is having a sum, here it is a difference and borrow. It is having difference and borrow, and having 3 inputs like A, B and C. Then I finding a relation here, whatever we have did. Similar manner, I am finding an outputs like 0 0 0 to 1 1 1. Why? Because 8 combinations, 3 inputs, 2 cube is 8. So I have found here. So difference and borrow outputs were founded. Okay, after that I'm finding a truth table for a difference. So here difference, when I'm drawing a K map for the difference, it is nowhere it is matching. which means that I need to be write in individual outputs like this. So A B C, A bar B bar C bar, A bar B C bar, A bar B bar C. Similarly, if I am taking an output for borrow, so I got A bar B plus A bar C plus B C. So this is an output I got. Then what is the step 3? I need to draw the logic circuit. Okay, here I am going to be simplified for difference like A XOR B XOR C, so you can understand this simplification like a boolean simplification, the same thing as earlier also we have did. So that is simplified expression, and the borrow or get a simplified expression. So I have drawn a logic circuit diagram like this. So which means that this particular diagram again tells that a full subtractor can able to design using a two half adders. Two half adders are added because here I'm using an OR gate. So OR gate is nothing but plus. So if I adding two half subtractors, then I can get my full subtractor output here. Okay. So hope you understood the full subtractor, as this is same as of full adder and half subtractor is similar. Only one difference is additional NOT gate is occurring here, A bar. Okay. So where case of half full adder, it won't be having any bar symbol here, then it is full subtractor. Okay, it is clear now. Okay, then we'll go for an actual topic is a code converters. Okay, so these are the code converters, which means that I have some inputs and some outputs, so that has to be converted. Just a minute. Yeah, now we are going to be discuss about code converters. So what is these code converters? What it means that, because we have seen various circuits in your first unit, conversion of binary to gray code, BCD to XS3 code, and binary to BCD code. So these are the conversions, how it can able to convert those things we have seen. But physically I need some circuit of a digital circuit which can able to convert. If I'm giving some binary input, it has to generate my XS3 output, or if I'm giving some BCD input, it has to generate some gray code. So I need to design this. So these are the code converters, are a combinational circuit which will perform such operation. One type of a code can be converted into the another type of a code. So that depends upon a problem statement, and the procedure of code converters or code converters of like a combinational circuit as similar to the procedure of a combinational circuit. Let's take an example. Okay, to convert a 4-bit binary number into a gray code, and you can do or you can practice at home for wise conversion of gray to binary. Okay, so here we'll discuss a 4-bit binary to gray code. This is a problem statement. I need a combinational circuit which can convert my 4-bit binary number into a gray code. Okay, so this is a code converter I required here. So I have some X code X that has to be converted as a code Y, where here code X is a binary, that to 4-bit binary, and code Y is a gray code. So now by this I understood that it have a 4 input variables, and when converting it is a 4 output variables. So this is a binary to gray code. So I'm taking 4 input variables like a B0, B1, B2, B3 indicates B indicates a binary value, and it is having a 4 outputs, that is gray code outputs, called G0, G1, G2 is a gray code outputs. So I have designed and I have named input and output variables. So the immediately to the next step is drawing a truth table. So here the drawing have designed a truth table, and which gives the relation between input and output. Here how it is converted, we know that procedure. Okay, how it is converted, we know the procedure. Okay, so converting of a binary to gray code. So based on that I have filled this particular table and I have drawn these outputs. Okay, once these outputs are found, now I need to be apply a Karnaugh map or any Boolean simplification method for individual outputs like G0, what is an minimal equation, G1, what is a minimum equation, G2, what is, and G3, what is a minimum equation. Okay, so that I'll explain once again if you want how it is converted. So if I want to convert any binary number into the gray code, the procedure is like this. Suppose I have 0 0 1 0 is my binary number. If I convert it to the gray code, how it will be? MSB as it is, I need to be right here. Okay, then I need to be add these two XOR operations. 0 plus 0 is 0. Again 0 plus 1 XOR operation is 1. So 1 plus the XOR operation 1. So 0 1 0, this is my binary output and this is my gray code. Similar manner, let us take one more example like 1101. So here I am taking 1101. So I am writing MSB as it is, 1 XOR 1 0, 1 XOR 0 1, 0 XOR 1 1. So 1 0 0 1 1, 1 0 1 1. This is your binary gray code output. Similar manner, I have filled this entire table because already we discussed in our previous conversion of binary to gray. We have discussed and we have formed this table. Just I have replaced the table here, that's all. Immediately next step, once formed, I need to be find an outputs. Okay, so these are the simplification. So G3, okay, if you see the table, all these are ones. So which means that in G3, if you see, G3, if you see 8, 9, 10, 11, 12, 13, 14, 15, these are the inputs are high. So G3 is a summation of, so I want to draw the K map for this. So for G3, this is I have drawn a K map. So while combining all these things, because we know that I can able to combine 8 variables here, okay, all B0. So here I have a B3 and B2, okay, B2. Here I have B3 R and B2, B3, B2 bar, B2. So I have a B3 is my output. Similar manner, G2, I have 4, 5, 6, 7, 8, 9, 10, 11. 4, 5, 6, 7, 8, 9, 10, 11. So these are the 4. So this is a 4-bit combination. This is a 4-bit combination K map. I got B3 XOR B2. And G1 is B2 XOR B1 and G0 is B1 XOR B0. So these are the ways I got an output. Then immediately once the K map simplification is done, I can go for outputs. So by my B0 is nothing but, what is your B0? Input is B0. Okay. So what is your B0? B0 is, so that is nothing but your G0 is, how you got? B0 and B1 XOR operation. So B0 and B1 XOR operation G0, LSB. G1 is B2 and B1. Okay, G3 is B3 and G2, and B3 is G3, as we did in the previous, the MSB of binary writing as it is. And now I need to do an XOR operation between B3 and B2, B1 and B2, B1 and B0. The same thing I have did. Now whatever this circuit we got, that is a code converter circuit. Okay, this is a code converter circuit. If I am giving some binary value, definitely that will give the corresponding gray code value. So at home, please try gray to binary conversion and whatever the circuit. Okay, so let me tell you one example how that will be gray to binary. Suppose I have a gray code value like 1101. So how the binary need conversion? MSB as it is I need to be right here. Then binary value XOR with an gray code value and I need to write here. So that 1 XOR 1 0, 0 XOR 1 0 and 0 XOR 1 1. This is, so which means that 1100 01 of a gray code is equivalent to 1001. So similarly the same outputs you can get. Okay, then we can go for another circuit called as an XS3 to BCD converter. So I know what is XS3 and what is a BCD and what is the starting value of XS3. So I need a circuit. I have named the input variables like E0, E1, E2, E3. Those are XS3 values, and I'll take an output value BCD like a B0, B1, B2, B3. So once the inputs and output variables are defined, then I have to be draw. So here the XS3 value starts from 3, so that 0, 4, 1, 2, 3, 4, like this 9. After 12, 0, 0, 0 is undefined, because in XS3 value starting value is 3, which means that M0 and M1 minterms, M2 minterms are not there, because minimum minterm starting with M3. So what these conditions I need to be take as a don't care conditions. Similarly, after 12, 13, 14 and 15 will not exist in your BCD XS3. So those things are considered as your don't care condition. So this is a table I formed. So then from the table I have taken Boolean expressions like B3 output is when a B3 output is only 11 and 12 M. Other things can consider as a don't care like M0, M1, M2, M13, M14. All these are considered for all the variables, all the output variables. These consider as your don't care values. So what is the need of considering don't care, sir? So because we have seen in a simplification of K-map using a don't care, if I include a don't care, so that my output expression can further reduced. Those don't care values, if it is useful for to reduction, use it, if not neglect it. Okay, same manner B2 have written B1 and B0. Okay, so then I found that B3 value. So I have B3 11 and 10. So other things are don't care. So by forming I can get B3 is equal to E3 E2 plus E3 E1 E0. Okay, this is an expression I got. Similarly then B2, this is an expression. Okay, B1 I got E1 bash plus E0 plus E1 E0. So how it will become, because it is a simple K-map I have used. Please try to do in your notebook so that you can analyze. Don't simply see that whether it is coming or not. Please check it and tell me. Okay, this is B0. So once these outputs are occurring, what is the next step? Immediately to next step, I have to be draw the logic circuits. I have these outputs here. Now I have to be draw output. I am taking, this is a table, I am taking E3 E2. So this is a logic diagram I have. Okay, don't confuse that it is very clumsy and it is showing many gates. So no, just you draw from B3 whatever the things are connected, connect it. Similarly B2 B1 B3. Okay, so if you take, I'll tell you one example here. B0 is nothing but E0. So here B0 is E0 bar. Okay, this is E0, right? This is connected to NOT gate, that is giving as your B0, E0 bar. Similar manner other things also took here. Then we'll go for one more circuit called as a magnitude comparator. Okay, so what is this magnitude comparator? It is called as a 2-bit comparator. Simply can say that two numbers compare. So when I'm comparing any two numbers, obviously you can say that number A is greater than B, or A is equal to B, or A less than B. These are the three different outputs are occurring. So now I have a two inputs, and the inputs may differ, because if I say 2-bit comparator, then 2 bits AB will be there. If it is n bit, so n inputs are there, but outputs is always same. Any comparator, whatever the inputs are there. So those outputs I am considering as a GT, which means that greater than, equal and less than. Okay, so these are the things. Greater than when is equal to, GT can go high when A is greater than B. EQ is nothing but A is equal to 1 when A is equal to B, and less than will is equal to 1 when A less than B. Okay, so for that I have drawn the table 0 plus 0, so which means that equal 0 1 lesser value, because A is 0, B is 1, so A less than B, other things are 0. 1 0, A greater than 1 1, both are equal. So I have formed a table here. So from this table I need to be draw a minimize. So if I take a equal comparator, I have a 0 0 1, I have 1 1 1. So that what means that it is an XNOR gate. So that what expression I got, A bar B bar plus AB, which is nothing but XNOR operation, or it can also say that XOR whole bar. So I use one XNOR gate, then simply I'll go for A B bar, so it is nothing but again less than A less than B, and A bar B bar, so A greater than B. So all together combinedly, so that I have the circuit like this. Here I am using AB input, XOR plus NOT gate, XNOR, A is equal to B is generating A greater than B, and A less than B is generating here. Okay. Similarly, 2-bit comparator, which means that it is having a 2 inputs. Okay, so the inputs are 2 inputs like A0 A1, B0 B1. So there are 2 bits are there, so I need to be compared. So the totally 4 bits are there, so I have a 16 combinations. So based on that 0 0 A 0 0, so that A is equal to B. 0 0 0 1, 0 0 means what is the value? 0 0 1 is nothing but what is the value? 1. So how it will be? Now A less than B, A less than B. Here 0 and 1, A less than B. Here 0 and 2, A less than B. Here 1 and 0. Sir, how you are taking? I am taking an equivalent binary decimal value. 0 1 is nothing but 1. Suppose here I am taking, this is 1 1 is nothing but 3, and here it is 2 1 0. So what is happening? A greater than B, so A greater than B. Like that I am going to be marked, and I have filled the following table, and I'll simplify again an expressions using K-map, and this is your final circuit of 2-bit comparator. Similar manner, we have a 4-bit comparator also. These are the 4 inputs that have A0 A1, so it is not required. Just remember this diagram, the same procedure we need to be follow for this. Okay, hope you understood the code converters. We have n number of varieties. Please practice at home. Okay, like other gray to binary, binary to gray, XS3 to binary, binary to XS3, and BCD to binary. Like that, n number of code converters are there. Practice it. If you have any queries, you can ask me. And this is an exercise problems I am giving. So your task is to design a combinational logic subsystem to decode an hexadecimal digit in the range of 0 to 9 and A to F, and drive the 7-segment display. So how the 7-segment display will be there? 7-segment display is look like this. Now this is, so you have, it is given that you need to write 1. In case of 7-segment display, this is 1. So the names will be given like this: A, B, C, D, E, F and G. In 7 segments, the 7 segments named as, so you have a 7 input variables. Okay, you have a binary values, 4 binary values. Output should be there, 1 in the sense B, C on, other should be off. Suppose 2 is nothing but like this, so A, B, C is not there, D, E, G, these things should be on, others. So try like this. So here I am giving that equivalence values, how A, B, C, D. A means, so correspondingly you draw a table and design a combinational circuit of hexadecimal of number 0 to 9 and A to F, for the 7-segment display, and also design a combinational circuit to convert the binary to BCD. So until happy reading. Thank you very much.